There's a popular open source library called LangChain that can create chatbots that, among other things, do Q&A over any website document in 3 lines of code. Here's an example of that from the LangChain docs. So from LangChain, document loaders, import web-based loader. From LangChain indexes, import vector index creator, loader. So we tell it to load a web page, for example, in this case, Paul Graham. He has great essays, great work, HTML. Interesting. So we just pointed to the website to fine-tune on. Brilliant. And then we create an index from it, from this loader, and I guess this loader could be a file, a local file, but in this case we refer, and then we should we just query it. Index.query. What should I work on? Five lines. I mean, I'm sure it's not only 5 lines, and you need to install things, and it won't install correctly, and then you install this library, then that library, and right. But let's assume we pass the installation phase, which output answers specific to Paul Graham's essay. We asked him, what should I work on? The work you choose should ideally have 3 qualities. It should be something you have a natural aptitude for, something you have a deep interest on, and something that offers scope to do great work. If you are unsure, you could start by working on your own projects that seems excitingly ambitious to you. It's also beneficial to be curious, try lots of things, meet a lot of people, read lots of books, and ask a lot of questions. When in doubt, optimize for interestingness. It's okay to guess and be wrong sometimes, as this can lead to discovering what you're truly good and or interested in. Note, if you're interested, you can try the chatbot built from program essays here. The first time you run this, it feels like pure magic. How the heck does this work? The answer is a process called Retrieval Augmented Generation, or RAG for short. It is a remarkably simple concept, though also has incredible depth and the details of its implementation. So it's both simple, but when we get to the actual implementation, it's going to be complex and deep. This post will provide a high-level overview of RAG, and we'll start from the big picture, retrieval augmented. The big picture workflow generation of what's happening, and zoom in on all the individual pieces. By the end of it, you should have a solid understanding of how those 3 magic lines of code works and all the principles involved in creating these Q&A chatbots. If you're a developer trying to build bots like this, you'll learn which knobs you can tweak and how to tweak them. If you're a non-developer hoping to use AI tools on your dataset, you'll gain knowledge that will help you get the most out of them. And if you're just curious mind, you'll hopefully learn a thing or two about some of the technology that appending our lives. Let's dive in. What is retrieval augmented generation? Retrieval augmented generation is the process of supplementing user input to a large language model like ChatGPT with additional information that you have retrieved from somewhere else. The LLM can then use that information to augment the response that it generates. The following diagram shows how it works in practice. Okay, so what do we see here? See here a question to a knowledge base. This is the retrieval. There is some relevant knowledge in here. So there is a big knowledge base, probably the original ChatGPT, and then there is also the relevant knowledge. This is the LLM. Okay. So we ask some knowledge base. We do a retrieval. We have the LLM. And then it returns the response. So this is the LLM. What is this relevant knowledge and knowledge base? The original text that we fed into the LLM. So the errors are going to question the LLM. But the interesting thing here is that the errors are also going into the relevant knowledge. So is the question, let's see in the answer, because I'm going to discover this with you. Is the question going to the relevant knowledge, then to the LLM to return the response? And I see also another arrow which goes directly to the LLM. So we have two arrows, one to the knowledge base and another one to the LLM. Okay, let's see the explanation. This requires some explanation. It starts with the user question. How do I do something? The first thing that happens is the retrieval step. This is the process that takes the user question and searches for the most relevant content from the knowledge base that might answer it. The retrieval step is by far the most important and most complex part of the RAG chain, but for now, just imagine a black box that knows how to pull out the best chunks of relevant information related to the user query. Can't we just give the LLM the whole knowledge base? You might be wondering why we bother with retrieval instead of just sending the whole knowledge to the LLM. One reason is that models have built-in limits. Okay, so the model is already built. We are not going to rebuild it. Once we gotten the relevant information out of the knowledge base, we send it along with the user question. Okay, so we get some relevant information from the knowledge base during the question. The LLM is already built. And we send it to the LLM. The LLM, most commonly ChatGPT, then reads the provided information and answers the question. So it's like we are sending it a big question. We are not just sending the question itself, we are sending something big to the LLM that contains both the question and the whole content. Pretty simple, right? Working backwards, giving an LLM extra knowledge to answer the question. So it's like I went to ChatGPT or Bard and typed in addition to my text, some additional context and then asked it to answer based on this information. We start at the last step, answer generation. That is, let's assume we already have the relevant information pulled from our knowledge base that we think answer the question. How do you use that to generate an answer? We have some relevant notion. How do we go directly to the LLM, we get a response. Whatever the relevant information. The process may feel like black magic, but behind the scenes, it is just a language model. So in broad strokes, the answer is just ask the LLM. How do you get an LLM to do something like this? We'll use ChatGPT as an example, and just like regular ChatGPT, it all comes down to the prompts and messages. So we're playing with the prompts here. That's all we do. Giving the LLM automatically, meaning we are playing with the prompts automatically, but let's see if there is something additional to it. Giving the LLM custom instructions with the system prompt. The first, we converted them also to a vector. Okay. The first component is the system prompt. The system prompt gives the language model its overall guidance. ChatGPT, the system prompt is something like a helpful assistant. In this case, we want it to do something more specific, and since it's a language model, we can just tell it what we want it to do. Here's an example short system prompt that gives the LLM more detailed instruction. You're a knowledge bot. You will be given the extracted part of a knowledge base, labeled with document, and a question. Answer the question using information from the knowledge base. We are basically saying, hey AI, we are going to give you some stuff to read. Read it and answer our question. Okay, thanks. And because AIs are great at following our instruction, it kind of works. Giving the LLM our specific knowledge sources. Next, we need to give the AI its reading material, and again, the latest AIs are really good at just figuring stuff out. But we can help it with a bit of structure and formatting. Here's an example format you can use to pass documents to the LLM. Document 1, some documents. Document 2, some documents. So we pass things, it's as if the AI is coming to life and we feed it with some knowledge and we give it some structure to the knowledge like a database. And then we ask it questions about this knowledge. It's interesting to see the structure that we give to the AI as prompt here. I mean, we label some parts of the text with document 1, then we label another part of the text with document 2, and we tell the LM document 1 is this. Do you need all this formatting? Probably not, but it's nice to make things as explicit as possible. You can, so we don't need all the formatting, but it's saying it's nice. What do we mean by nice? Let's see. You can also use a machine readable format like JSON or YAML, or if you're feeling frisky, you can just dump everything in a giant blob of text, but having some consistent formatting becomes important in more advanced use cases. For example, if you want LLM to cite its sources. Once we formatted the documents, we're just sending as normal chat messages to the LLM. Remember, in the system prompt, we told it we were gonna give it some documents, and that's all we are doing here. Putting everything together and asking the question. Once we've got our system prompt and our document messages, we just send the user's question to the LLM alongside them. Here's how that looks. OpenAI, we send it some messages, get system prompt. So we send it some messages. Yeah, we send it some messages with the JSON to the OpenAI. This is how its model looks like. It's a JSON with a version of the model and with a couple of messages here, and these are just functions that return our text. That's it, a custom system prompt, 2 messages, and you have context-specific answers. This is a simple use case and it can be expected to improve on. One thing we haven't done is told the AI what to do if we can't find an answer in the sources. We can add these instructions to the system prompt typically, either telling it to refuse to answer or to use its general knowledge. Depending on your bot's desired behavior, you can also get the LLM to cite the specific sources used to answer the question. We'll talk about these tactics in future posts. With the easy part out of the way, it's time to get back and to the black box we skipped over, the retrieval step, getting the right information out of your knowledge base. Above, we assumed you had the right knowledge snippets to send to the LM, but how do we actually get these from the user question? This is the retrieval step, and it's the core piece of infrastructure with chat with your data. So we extract from the knowledge base some relevant knowledge that we send to the LM. At its core, the retrieval is a search operation. We want to look up the most relevant information based on the user input, and just like search, there are 2 main pieces: indexing, turning your knowledge base into something that can be search queried, to querying, pulling out the most relevant bits of knowledge from search term. It's worth noting that any search process could be used for the retrieval. Anything that takes user input and returns some results would work. So for example, you could just try to find a text that matches the user's question and send that to the LLM. You could use Google to on the question and send top results across, which incidentally is an approximation how Bing chatbots work. Interesting. So they say that probably how Bing chatbots works is that it does some search for the relevant information, returns it, and then it asks the LLM with that context in mind, return the answer. That said, most RAG systems today rely on something called semantic search, which uses another core piece of AI technology, embeddings. Here we'll focus on the use case. So what's our embeddings? What are embeddings and what they do have to do with the knowledge retrieval? LLMs are weird. One of the weirdest things about them is that nobody really knows how they understand language. Embeddings are a big piece of the story. If you ask a person how they turn words into meaning, they will likely fumble around and say something vague and self-referential like "because I know what they mean." Somewhere deep in our brains there is a complex structure that knows child and kid and basically the same. Red and green are both colors, and pleased, happy, and elated represent the same emotion with varying magnitudes that we can't explain how this works, but we just know it. Language models have a similar concept understanding language, so they understand numbers, except since their computer is not their brains, but they are made up of numbers. In an LLM world, any piece of human language can be represented as a vector, list of numbers. This vector of numbers is an embedding. A critical piece of LLM technology is a translator that goes from human word language. We need to translate it to numbers, to AI number language. We call this translator an embedding machine. True, under the hood, it's just an API call. Human language goes in, numbers go out. Human language goes in, and numbers go out. What do these numbers mean? No human knows. They only are meaningful to the AI. But we do know is that similar words end up with similar set of numbers because behind the scenes the AI uses these numbers to read and speak. So the numbers have some kind of magic comprehension baked into them in AI. Even if we don't understand it, the embedding machine is our translator. Now, since we have these magic AI numbers, we can plot them. A simplified plot of the above example might look something like this, where the axes are just some abstract representation of human AI language. Good morning, how are you? So all these are related, and like cupcakes is less related. Once we plotted them, we can see that the closer 2 points are to each other in this hypothetical language space, the more similar they are. Hello, how are you? And hey, how is it going? Are practically on top of each other. Good morning, another greeting is not too far from those, and I like cupcakes is on totally separate island from the rest. Naturally, you can't represent the entire human language on two-dimensional plot, but the theory is the same. In practice, embeddings have many more coordinates, 1,500 for the current model used by OpenAI, number of dimensions, but you can still do basic math to determine how close two embeddings and therefore two pieces of text are one from another. These embeddings that determining closeness are the core principle behind semantic search, which powers the retrieval step. Finding the best pieces of knowledge using embeddings. Once we understand how search with embeddings works, we can construct a high-level picture of the retrieval step. On the indexing side, first we have to break up our knowledge base into chunks of text, knowledge snippets. This process is an entire optimization problem in of itself. We'll cover it next, but for now just assume we know how to do this. Once we have done this, we pass each knowledge snippet through the embedding machine, which is actually an OpenAI or something similar API. There is an API to create embedding. And get back our embedding representation of the text. Then we save the snippet along with the embeddings in a vector database. A database that is optimized working with vectors numbers. So we generate embeddings, knowledge snippet, we first split the text, generate embeddings, get embeddings, put them in vector database, both with the knowledge snippets. Now we have a database with the embeddings of all our content in it. Conceptually, you can think of it as a plot of our entire knowledge base and our language graph. Yeah, so we have the snippets as embedded in numbers, vectors. Once we have this graph on the query side, we have similar process. First, we get the embeddings of the user input. Yeah, this is the embedding of the question, turned into numbers. Then we plot it in the same vector space and find the closest snippets. So we put here the embedding of the question. Now we know that these two snippets are the closest, so maybe let's send only them to OpenAI. The magic embedding machine thinks these are the most related answers to the question that was asked. So these are the snippets that will pull out and send to the LLM. In practice, this is what the closest points question is done via a query into our vector database. So the actual process looks more like this. How do I do X? Embedding machine, embedding, vector database, and relevant knowledge. Yep. The query itself involves some semi-complicated math, usually using something called the cosine distance Though there are other ways of computing it, the math is a whole space you can get into it, but is out of the scope for the purpose of this post, and from practical perspective can largely be offloaded into a library database. Back to LangChain. In our LangChain example from the beginning, we have now covered everything done by this singular line of code. That little function call is hiding a lot of the complexity. Indexing your knowledge base. Alright, we're almost there. We now understand how we can use embeddings to find the most relevant bits of our knowledge base, pass everything to the LLM, and get our augmented answer back. The final step we'll cover is creating that initial index from your knowledge base. In other words, the knowledge splitting machine from this picture. Perhaps surprisingly, indexing your knowledge base is usually the hardest and most important part of the whole thing, and fortunately it's more art than science. It involves lots of trial and error. Big picture, the indexing process comes down to two high-level steps. Loading, getting the contents of your knowledge base out of whatever it is normally stored. Splitting up the knowledge into snippet-sized chunks that work well with embedding searches. Technical clarification. Technically, the distinction between loaders and splitters is somewhat arbitrary. You could imagine a single component that does all the work at the same time, or break the loading stage into multiple subcomponents. That said, loaders and splitters are how it's done in LangChain, and they provide a useful abstraction on top of the underlying concepts. Let's use my own use case as an example. I wanted to build a chatbot to answer a question about my SaaS boilerplate product, Pegasus. The first thing I wanted to add to my knowledge base was the documentation site. The loader is the piece of infrastructure that goes to my docs, figures out what pages are available, and then pulls down each page. When the loader is finished, it will output individual documents, one for each page of the site. Inside the loader, a lot of is happening. We need to crawl all the pages. Standard programming. We're back to the crawling of web pages. Scrape each one's content and then format the HTML into usable text, and loaders for the other things. PDFs or Google Drive have different pieces. There's also parallelization, error handling, and so on to figure out. Again, this is a topic of nearly infinite complexity, but one that will mostly overload to a library for the purpose of this write-up. So for now, once more, we'll just assume we have this magic box where knowledge base goes in and individual documents comes out. LangChain loaders. Built-in loaders are one of the most useful pieces of LangChain. They provide a long list of built-in loaders that can be used to extract content from anything from a Microsoft Word to an entire Notion site. The interface to LangChain loaders is exactly the same as depicted above. A knowledge base goes in and a list of documents goes out. Coming out of loaders, we'll have a collection of documents corresponding to each page in the documentation site. Also, ideally, at this point the extra markup has been removed in just the underlying structure, and text remains. Now we could just pass these whole web pages to our embedding machine and use those as our knowledge snippets. But each page might cover a lot of ground, and the more content in the page, the more unspecific the embedding of that page becomes. This means that our closeness search algorithm may not work well. What's more likely is that the topic the user question matches some piece of text inside the page. This is where splitting enters the picture. With splitting, we take any single document and split it up into bite-sized embeddable chunks better suited for searches. Take one document, split it to document snippets, because the answer might be in some of them or relevant to some of them. Once more, there's an entire art to splitting up your document, including how big to make the snippets. On average, too big and they don't match the queries well, too small and they don't match enough useful context to generate answers. How to split things up, usually by headings, and if you have them, and so on, but a few sensible defaults are good enough to start playing and refining your data. Splitters in LangChain. In LangChain, splitters fall under a larger category called document transformers. In addition to providing various strategies for filling out documents, they also have tools for removing redundant content, translation, adding metadata, and so on. We only focus on splitters here as they represent the overwhelming majority of document transformations. Once we have the document snippets, we save them into our vector database as described above, and we're finally done. Here's the complete pictures of indexing. We come from a knowledge base, we load them, we get the different documents, the text, we split them, we get document snippets, we turn it into a embedding machine and get the embedding and put it in a vector database together with the original text. Back to LangChain. In LangChain, the entire indexing process is encapsulated in these two lines of code. First, we initialize our website loader and tell it what content we want to use. Loader is web-based loader with the URL. Then we build the entire index from the loader and save it into the vector database. Index, vector, index creator from loaders. The loading, splitting, embedding, and saving is all happening behind the scenes. Recapping the whole process. At last, we can fully flesh out the entire RAG pipeline. Here's how it works. Loading, splitting, embedding, vector database. Question comes. Go to the embedding machine in order to translate the question into embedding. Find the closest snippets in the vector database to the embedding of the question. Send them, both them and the question, to the LLM and get back the answer. Now it's clear. First, we index our knowledge database. We get the knowledge and turn into individual documents using a loader, and then you use a splitter to turn it into bite-sized chunks or snippets. Once we have those, we pass them to our embedding machine, which turns them into vectors that can be used for semantic searching. We save these embeddings alongside the text snippets into our vector database. Next comes retrieval. It starts with a question, which is then sent through the same embedding machine and passed into our vector database and to determine the closest matches snippets which we'll use to answer the question. Finally, augmented answer generation, where we take the snippets of the knowledge, format them alongside the custom system prompt, the question, and finally get a context-specific answer. Wow! Hopefully, you now have a basic understanding of how retrieval augmented generation works. Definitely, we have this basic understanding. If you'd like to try out on a knowledge base of your own without all the work of setting up, check out Scrive.ai, which lets you build domain-specific chatbots in just a few minutes, with no coding skills required. In future posts, we'll expand on many of these concepts, including all the ways you can improve on the default setup outlined here. As I mentioned, there is nearly infinite depth to each of these pieces, and in the future we'll dig into those one at a time. If you'd like to be notified when those posts come out, sign up. I don't spam, and you can subscribe whenever you want. Yeah, so this was super interesting. I think that in addition to calling up, if we are concerned about privacy, then instead of going to OpenAI LLM, then we have this 10 gigabyte or whatever, 30 gigabyte or 7 gigabyte LLM that we can host locally. And then we can close this whole loop locally. And I think there is another method of fine-tuning a model. I wonder, this is not, I think, fine-tuning a model. This is giving the model additional information and returning the response. Okay, so we need to read another post in order to understand what is fine-tuning a model, whether it's this. I think this is just RAG, as they say it. This is just this is a different process, I think. Retrieval augmented generation, they didn't specify here fine-tuning, but this looks extremely well. So if you have public information, this is perfect. If the information for your company documents or documentation is publicly, this looks perfect. It's public, it's already over the internet. If the information is private, then we'll need to host the LLM somehow locally. But the process still should be simple, because instead of web-based loader, first we load the local file, pretty sure they have such a loader, and then we need to point it somehow to a local LLM. But now that we understand the process, we are better shaped into doing this. So this was how do domain-specific chatbots work on an overview of retrieval augmented generation.